All right, let's go.
Number 12, C-type asteroids, the most common rock in the solar system. If you picked a random asteroid from the asteroid belt, there is roughly a 75% chance it would be this: C-type asteroids, carbonaceous asteroids, the most abundant type in the solar system, and some of the most scientifically valuable objects we have ever studied. They are dark, extremely dark. Their surfaces reflect only 3 to 9% of the light that hits them, making them blacker than coal. From Earth, they are nearly invisible against the darkness of space, despite being enormous. Some C-type asteroids are hundreds of kilometers across. The darkness comes from their composition. C-type asteroids are rich in carbon compounds, organic molecules, and water-bearing minerals called hydrated silicates. They are essentially unchanged since the formation of the solar system 4.6 billion years ago. They did not melt, they did not differentiate, they did not experience the geological processing that erased the early history of planets like Earth. Studying a C-type asteroid is studying the raw material of the solar system before planets existed. JAXA's Hayabusa 2 mission returned samples from Ryugu, a C-type asteroid, in 2020. The samples contained amino acids, the building blocks of proteins, the building blocks of life, delivered from space in pristine 4.6 billion-year-old rock. The current leading theory for how Earth got its water involves C-type asteroids. Early in solar system history, a bombardment of water-rich, carbonaceous asteroids delivered the oceans. Every drop of water ever drunk by every living thing on this planet may have arrived on a C-type asteroid. Number 11, S-type asteroids, the rocky ones closest to home. S-type asteroids, silicaceous or stony asteroids, make up roughly 17% of the asteroid population. They are the second most common type and the most common in the inner asteroid belt, the region closest to Earth. Where C-types are dark, S-types are bright. They reflect 15 to 25% of incoming sunlight, making them much easier to spot from Earth. Their composition is primarily silicate minerals, olivine, pyroxene, mixed with nickel-iron metal, similar to the rocky mantle of Earth but never melted and differentiated the way Earth's interior did. S-type asteroids are the source of the most common type of meteorite found on Earth, ordinary chondrites. When you hold a meteorite in your hand, the kind sold in mineral shops, the kind displayed in natural history museums, there is a good chance you are holding a piece of an S-type asteroid. NASA's Near Shoemaker mission orbited and then landed on Eros, a large S-type asteroid, in 2001, the first spacecraft to land on an asteroid. Eros is 34 kilometers long and shaped roughly like a potato. JAXA's original Hayabusa mission returned samples from Itokawa in 2010, the first asteroid sample return in history. Itokawa turned out to be a rubble pile, not a solid object, but a loose collection of boulders and gravel held together by its own weak gravity. Many asteroids are like this, less a solid object than a cloud of rubble in a slow gravitational embrace. Number 10, M-type asteroids, the metal worlds. M-type asteroids are relatively rare, a few percent of the total asteroid population, but they are potentially the most economically significant objects in the solar system. They are made primarily of nickel and iron, solid metal, not rock with metal inclusions, metal all the way through. The most famous M-type asteroid is 16 Psyche, a roughly 220-kilometer-wide metallic body in the outer asteroid belt. Psyche is thought to be the exposed iron-nickel core of a protoplanet, an early solar system body that was in the process of differentiating into a core and mantle when it was catastrophically destroyed by a collision. What remains is the core, naked, drifting in the asteroid belt for 4.6 billion years. The estimated metal content of Psyche, if extracted and sold at current commodity prices, has been valued at somewhere around $10 quintillion, more than the entire global economy by a factor of millions. NASA launched the Psyche spacecraft in 2023. It is currently en route to the asteroid and will arrive in 2029. Nobody has ever visited a metallic world. We do not know exactly what to expect. What we do know is that Psyche may be our only opportunity to study the deep interior of a planet-like body directly. Earth has an iron-nickel core. We have never reached it. We have never sampled it. Psyche may be the closest thing we ever get. Number 9. V-type asteroids. Pieces of a broken planet. V-type asteroids are not classified by composition alone, but by their origin. They are fragments, specifically fragments of the giant asteroid Vesta, the second largest body in the asteroid belt at 525 kilometers in diameter. Vesta was large enough early in solar system history to partially differentiate, to develop a layered internal structure with a distinct crust, mantle, and core. It was on its way to becoming a proper planet when the solar system's early chaos intervened. A massive collision tore a chunk out of Vesta's south pole, creating a crater so large it is visible from Earth through a telescope. The debris from that collision scattered across the inner solar system, becoming the V-type asteroids. Some of that debris reached Earth as meteorites. The HED meteorites, Howardites, Eucrites, Diogenites, found in Antarctica and elsewhere on Earth, are fragments of Vesta that have been sitting in our museums and collections for decades. We have had pieces of Vesta in our hands for a long time without fully appreciating what they were. NASA's Dawn spacecraft orbited Vesta from 2011 to 2012 before moving on to Ceres. The imagery revealed a world of dramatic topography, mountains, craters, and geological complexity unexpected in an object that small. Number 8. Near-Earth asteroids, the ones that concern us. Near-Earth asteroids are not a compositional type. They are a dynamical class, defined by their orbital path rather than what they are made of. They are asteroids whose orbits bring them close to Earth's orbital path. There are 3 main subgroups. Atins have orbits mostly inside Earth's orbit. They spend most of their time between Earth and the Sun and cross Earth's orbit on the outside. Apollos have orbits that cross Earth's orbit with a period greater than 1 year. Amors have orbits that approach but do not cross Earth's orbit. By 2026, we have cataloged over 35,000 near-Earth asteroids. The total population of near-Earth asteroids larger than 140 meters, big enough to cause regional devastation, is estimated at around 25,000. We have found and tracked roughly 40% of them. The other 60% are unknown, untracked, moving through the inner solar system on orbits we have not yet calculated. NASA's DART mission in 2022 demonstrated that we can deflect an asteroid. The spacecraft impacted Dimorphos and measurably changed its orbital period, the first time humanity has intentionally altered the motion of a celestial body. Apophis, a 340-meter Apollo-class near-Earth asteroid, will pass within 31,000 kilometers of Earth on April 13, 2029. Visible to the naked eye, closer than geostationary satellites. Safe, current calculations rule out impact for at least 100 years, but 31,000 kilometers on a cosmic scale is essentially a near miss. Number 7. Trojan Asteroids, the hitchhikers riding with the planets. Trojan asteroids are not found in the asteroid belt. They travel in the same orbit as a planet, leading it or following it by 60 degrees, locked in stable gravitational positions called Lagrange points. Jupiter has the most, roughly 10,000 known Jupiter Trojans, and the estimated total population may rival the main asteroid belt. They sit 60 degrees ahead of Jupiter in the L4 Lagrange point, the Greek camp, and 60 degrees behind in the L5 point, the Trojan camp. These are not small rocks. Some Jupiter Trojans are hundreds of kilometers across. They have been in their current orbits for billions of years, gravitationally trapped early in solar system history, possibly during the orbital migrations of the giant planets described in the Nice model. Earth has Trojans too, small ones. The largest, 2010 TK7, is roughly 300 meters wide and leads Earth in its orbit by 60 degrees. It is the first Earth Trojan ever confirmed. Mars has Trojans. Neptune has Trojans. Even Venus may have small Trojan companions. NASA's Lucy mission launched in 2021 and is currently making its way through the solar system on a complex trajectory that will visit 8 different Trojan asteroids by 2033, the first mission ever to study Jupiter's Trojans directly. Number 6. Main Belt Asteroids, the graveyard of an unbuilt planet. The asteroid belt between Mars and Jupiter contains hundreds of thousands of asteroids ranging from dust grains to Ceres, a dwarf planet 940 kilometers across. For a long time, the popular explanation was that the asteroid belt was the remnant of a planet that was destroyed, blown apart by some ancient catastrophe. This is wrong. The asteroid belt is the remnant of a planet that never formed. Jupiter's gravitational influence prevented the material in that region from accreting into a single body. Every time planetesimals tried to clump together, Jupiter's gravity stirred the region, increasing orbital velocities and turning gentle accretion collisions into violent impacts that broke things apart rather than building them up. The total mass of the asteroid belt today is roughly 4% of the Moon's mass. Tiny, spread across an enormous volume of space. The gaps between asteroids are vast. Spacecraft can fly through the belt without hitting anything. The asteroid belt is not a dense, dangerous field the way science fiction portrays it. It is mostly empty space with occasional rocks spread across a region spanning hundreds of millions of kilometers. Ceres, the largest body in the belt, was classified as a planet when discovered in 1801, then reclassified as an asteroid, then reclassified as a dwarf planet in 2006, when Pluto got the same treatment. Ceres has a differentiated interior, a rocky core surrounded by an icy mantle, and shows evidence of past hydrothermal activity. Bright spots in Okator crater are salt deposits left by briny water that was exposed to the surface and evaporated. A world that should not be interesting turns out to be fascinating. Number 5. Short-period comets, the visitors with a schedule. Now we leave asteroids and enter the world of comets. And comets are different in almost every way. Where asteroids are rock and metal, comets are ice. Frozen water, carbon dioxide, carbon monoxide, methane, ammonia, mixed with dust and organic compounds. When a comet approaches the sun, this ice sublimates directly from solid to gas, vaporizing without becoming liquid, and the resulting gas and dust form the coma and tail that make comets visually spectacular. Short-period comets, defined as comets with orbital periods of less than 200 years, originate in the Kuiper belt, the region of icy bodies beyond Neptune. Gravitational interactions with the giant planets nudge these objects into the inner solar system, where they develop their characteristic tails and become visible from Earth. The most famous short-period comet is Halley's Comet, orbital period 75 to 76 years. Last apparition, 1986. Next apparition, 2061. At the 2061 return, it will be significantly more favorably positioned than in 1986 and should be much more impressive. Comet 67P Churyumov-Gerasimenko, the target of ESA's Rosetta mission, is a typical Jupiter family short-period comet with an orbital period of 6.4 years. Rosetta orbited 67P for 2 years and deployed the Philae lander in 2014. The images revealed a bizarre rubber duck-shaped object, 2 lobes joined by a narrow neck, covered in jets of gas and dust erupting from active regions on its surface. The surface of 67P turned out to be not soft and fluffy as expected, but covered in hard, consolidated material, sintered dust cemented together by repeated heating and cooling. The interior was surprisingly porous, roughly 70% empty space. Nothing about 67P looked like the models predicted. Number 4. Long-period comets, the strangers from the edge of the solar system. Long-period comets have orbital periods exceeding 200 years. Some have periods of millions of years. They come from the Oort cloud, the vast spherical shell of icy bodies surrounding the solar system at distances between 2,000 and 100,000 astronomical units from the Sun. The Oort cloud has never been directly observed. It is inferred from the orbital characteristics of long-period comets, the directions they arrive from distributed uniformly across the entire sky, and the shapes of their orbits indicating origins at enormous distances. It is estimated to contain trillions of icy bodies. Long-period comets arrive in the inner solar system essentially without warning. A comet with a million-year orbital period has not been observed before in human history. It arrives new, unknown, with no prior apparition to calibrate predictions against. This makes long-period comets both the most spectacular and the most unpredictable of all comets. Their behavior as they approach the sun for the first time can be dramatically different from comets that have made the journey before, because all the most volatile ices are still present on their surfaces, having never been exposed to solar heating before. Comet Kohatek in 1973 was predicted to be spectacular, billed as the comet of the century, and was a disappointment because its brightness did not develop as expected for a first-time visitor. Comet Ison in 2013 was similarly anticipated and ultimately disintegrated as a past perihelion, the closest approach to the sun. Long-period comets are the wild cards, magnificent or nothing. You never know until they arrive. Number 3. Sungrazing comets, the ones that fly through the sun's atmosphere. Sun-grazing comets pass so close to the sun during perihelion that they travel through the solar corona, the sun's outer atmosphere, at distances of less than 50,000 kilometers from the solar surface. Most do not survive. The Kreutz sun-grazers are the most famous family, a group of comets all sharing similar orbital characteristics because they are fragments of a single giant comet that broke apart thousands of years ago. SOHO, the Solar and Heliospheric Observatory, has discovered over 4,000 Kreutz sun-grazers since 1996. Most are small, a few meters to tens of meters across, and they simply evaporate as they approach the sun. SOHO detects them by watching them appear and then disappear in its coronagraph images. Occasionally, a sun-grazer survives. Comet Lovejoy in 2011 passed through the solar corona at a distance of about 140,000 kilometers from the solar surface, well within the corona, and emerged intact. Astronomers watching in disbelief as it flew directly through conditions that should have destroyed it within seconds. It survived because it was large enough, roughly 500 meters across, that its nucleus retained enough volatiles to keep going despite the extreme heating. SOHO and STEREO have revolutionized our understanding of sun-grazing comets, discovering hundreds per year that ground-based telescopes would never see. Citizen scientists examining SOHO data online have discovered hundreds of previously unknown sun-grazers. A solar observatory designed to study the sun has accidentally become the most prolific comet hunting instrument in history. Number 2. Interstellar comets and asteroids. The visitors from another star system. In October 2017, Oumuamua arrived, the first confirmed interstellar object, an object from another star system, ever detected passing through our solar system. In 2019, Comet Borisov arrived, the second confirmed interstellar visitor. Unlike Oumuamua, which showed no visible outgassing and behaved strangely, Borisov looked completely normal, a comet, with a coma, with a tail, sublimating as comets do, just from another star system. Borisov was remarkable precisely because it was unremarkable. Its composition, analyzed by multiple telescopes, turned out to be similar to solar system comets: water ice, carbon monoxide, standard comet stuff. This suggests that the chemistry of comet formation is not unique to our solar system. The same processes that built our comets built comets around other stars. The estimated rate of interstellar objects passing through the inner solar system suggests that at any given time, roughly one interstellar object is within the orbit of Saturn. We just cannot see most of them. They're too small and too fast. The Vera Rubin Observatory, coming online in the late 2020s, will survey the entire sky with unprecedented depth and cadence. Its detection capability will find interstellar visitors much earlier in their approach, giving us time to study them properly, perhaps even with sufficient advance notice and a very fast spacecraft to send a probe to intercept one while it is still in the solar system. A sample return from an interstellar comet would be the most significant scientific mission in human history. Number 1. Centaurs, the hybrid objects that cannot make up their minds. Centaurs occupy the strangest middle ground in the solar system. Named after the mythological half-horse, half-human creatures, they are hybrid objects with characteristics of both asteroids and comets. Their orbits cross the paths of the giant planets, unstable by definition, destined to be ejected from the solar system or thrown into the inner solar system within a few million years. The first confirmed centaur, Chiron, was discovered in 1977, orbiting between Saturn and Uranus. Initially classified as an asteroid, then in 1988 it developed a coma, a cloud of gas and dust surrounding it like a comet, an asteroid growing a comet tail. Chiron was reclassified as both a comet and an asteroid simultaneously. It holds both designations today. Centaurs are thought to be Kuiper belt objects that have been gravitationally scattered inward by Neptune and are now in unstable transitional orbits. They are the link between the outer solar system reservoir of icy bodies and the short-period comets of the inner solar system. Every Jupiter family comet was once a centaur. Every centaur was once a Kuiper belt object. Some centaurs are enormous. Chariklo, the largest known centaur, at roughly 250 kilometers across, was discovered in 2014 to have its own ring system. Rings around a centaur, not around a planet, around an object smaller than many asteroids that is itself in an unstable orbit between the giant planets. The solar system keeps finding new ways to be stranger than expected. 12 types of asteroids and comets, from the carbon-rich time capsules that delivered our oceans to the metal worlds that are the naked cores of ancient planets, from the short-period comets on reliable schedules to the long-period visitors arriving for the first and only time, from sun-grazers flying through the sun's own atmosphere to interstellar wanderers from other star systems entirely. The solar system is not a simple place, and most of it is still waiting to be properly explored. Subscribe to Cosmic Hives. See you in the next one.